Hi guys, welcome back to 7 Steps to a 7 in Olympiad Geometry. In this video, we're going to be looking at applications of what we have learned in the course so far. Because in the last 5 videos, we have explored basically all the necessary concepts to solve easy to medium Olympiad geometry problems, such as angle chasing, power of a point, lengths, and homothety. And in this video, we're going to be applying all of them to look at very special configurations. But first, before we get into the new configurations, let's review the old ones. So in the past many handouts, I provided many important configurations as part of the examples or exercises, and hopefully by now you've had a chance to go through them. But if not, then that's totally fine. Just see if you can try to prove each of these configurations on your own. And if you need any help on it, or if you're stuck on trying to prove something, let me know in the comments what your progress is so far, and I'll do my best to guide you on the right track. All right, so what are these configurations that we need to know? So first, we have the orthocenter configuration. So suppose we have a triangle ABC here. So ABC. Then we have the theta, the altitudes, D, E, and F. And we also have the orthocenter H. And we even have the midpoints M, then N, then P. And also the midpoints of these segments, A1, B1, and C1. All right, so what do we know about this orthocenter configuration? Well, one thing we know from the first video is that because all of these are 90 degrees, BFEC is cyclic, and its circumcenter is the point M by Thales' theorem. And similarly, the circle, we have that AEHF is cyclic, and the circumcenter is A1, again by Thales' theorem. And then we have that if we actually draw the circle in, so now instead of considering that as cyclic, we draw in the circle, we have that MF and ME are tangents to the circle. So let me draw those in red. And we also have that the line through A parallel to BC is also tangent to the circle. So this is called 3 tangents. Okay, so that's 3 tangents. Then we have that whenever we reflect the orthocenter H across the side BC, suppose that it ends up at this point H prime, then H prime lies on the circumcircle of the triangle ABC. So there it is. And we also have that when we reflect the point H across M, we end up getting, so that's that. Then we end up getting a point A prime, such that AA prime here is a diameter of the circumcircle. So this is called orthocenter reflection. Okay, so we have a few final facts. So if the triangle is acute, as it is in this case, then we know that H is the incenter of the triangle DEF. And recall from the second video that I made that the ABC has to be acute in order for H to actually be the incenter. And in fact, if ABC is not acute, then H is something known as an excenter instead. But more on that later. And finally, the last property we need to know about is that we have all 9 of these points here, D, E, F, M, N, P, and A1, B1, C1. They're all concyclic on the 9-point circle. And this 9-point circle is a result when you take a homothety centered at H of scale 1/2 and find the image of the circumcircle. So we're just taking this circumcircle and scaling it down by a factor of 2. So this is a 9-point circle. Okay, so be sure to know this orthocenter configuration. These are the most important things to know, and these are often tested a lot. Here's another configuration, this time involving the incenter. So suppose that we have a triangle ABC, and we have this incenter I. It's the intersection of the angle bisectors. Then if we draw in this circumcircle here, so let me draw it there. And if we draw in this circumcircle here, the center of this circle, which is this point here, lies on the circumcircle of the triangle ABC. So one circumcenter lies on the other circumcircle. And moreover, it also lies on this angle bisector here. And this is known as the incenter excenter lemma. So incenter excenter lemma. And you'll see why it's called the excenter lemma and why there's an excenter in here in a bit. Because it actually is tied into what is known as an excenter. Okay, so let's see what other theorems we have. The other two theorems we have that are useful for configurations are not really any configuration-based ones, but they're more auxiliary theorems. So let's first start with this one that you might remember from the second handout examples. So suppose we have triangle ABC, and you have points D, E, and F on the sides. Then all these three circumcircles, AEF, BFD, and CDE, I'll draw that a bit better. They all meet at this one point, P here. And this point P is known as the Miquel point of the system. So it's very useful to know that these 3 points are, these 3 circles are concurrent, as it can tell us a lot. Okay, and one final thing, and this is also very, very common. So let ABC be a triangle, and suppose that D is a point in the plane. Then if the feet of these altitudes here, so these are the feet of the altitudes, so I'll call them P, Q, and R, suppose. If all of them are collinear, in this diagram they're not, but suppose they are, then the circle ABCD is cyclic. So P, Q, R are collinear. They all lie in the same line. If and only if A, B, C, and D are concyclic. And this is very, very powerful. In fact, the line connecting P, Q, and R, if they are concyclic, is known as the Simpson line. All right, so now that we've explored some of these basic configurations, we can now look at some more complicated ones. Okay, when I was going through the review theorems, I mentioned that there's something called an excenter, where the excenter is in the incenter excenter lemma. So what exactly is this excenter here? Well, it's actually a very, very important triangle center, and you need to know all about it. But thankfully, it has very, very similar properties to the incenter. So let's get into it. So suppose that we have our triangle ABC once again. So A, B, and C. Then if we extend these lines, then there's another angle bisector other than this one here. Because even though this line here cuts these 2 lines here in half, the area in here, we can also cut these 2 lines in half, like the area in between, by going in between these ones instead. So this line here is known as the external bisector. And if we construct the other external bisector, they intersect at this very funny point outside of the triangle. And this point is known as the A excenter. So A excenter. And you would expect that it would also lie on the internal angle bisector by very similar reasons for why the incenter exists. And indeed it does. the excenter is the intersection of these two external angle bisectors and this main internal angle bisector. And just like with the incenter is somewhere here, and it has this circle, the incircle. The excenter has another circle tangent to all three sides. So the incircle is not the only one. And this circle out here is known as the AX circle. All right, so because we know about this excenter now, we want to figure out its properties. So suppose that we get rid of our excenter from the picture, and I'm an excircle. And then we construct the other two excenters. So we have, and then here's the last one here. So this is the point IB, and this is the point IC. And we have the line CIC and BIB, and they all meet at the point I. Then what exactly do we know about this configuration? Well, for starters, we know that all these 3 points, A, IC, and IB, lie on the external angle bisector of angle BAC. So that means that A, IB, IC are all collinear. And therefore, we have the other sides are collinear as well. And because this external bisector is perpendicular to this internal angle bisector, because they just meet at a right angle here, and you can just calculate it on your own, we get that IAI is perpendicular to IBIC. And this holds for the other three sides as well. So it's perpendicular to IAIC, and ICI is perpendicular to IAIB. And therefore, we have that I is the orthocenter of the triangle. Orthocenter of the triangle IAIB, IC. Okay, cool. So now let's see what happens when we draw in the circumcircle of the triangle ABC. So let's go ahead and draw this in. I'll draw it in a different color so that you can see what's going on. So I draw here. So now note that we're drawing a circle through the feet of the altitudes here. So A is the foot of the altitude from IA to IBIC, and so similarly for B and C. So therefore, this means that we're drawing the circumcircle of the triangle formed by the feet of the altitudes. And this triangle should be familiar from the configuration review I did earlier. In other words, this circle here is just the 9-point circle of IA, IB, IC. So if I draw the circle slightly better, so then it should be something like this. Then this circle here is a 9-point circle. And as such, we have some very, very profound consequences. And I'll leave a lot of them for you to deduce on your own, but one of them I want to point out in particular is that the midpoint of IA, which I'll call M here, this is the midpoint of this side here, and therefore it lies on the 9-point circle. So we have that IM equals MIA, and M lies on the circumcircle. However, this point M should look familiar to you from earlier, because we have that BICIA is cyclic, because both of these angles are 90 degrees. And M is its circumcenter, and it lies on the 9-point circle. In other words, the circumcenter of BIC, this triangle here, lies on the circumcircle. And this is exactly the incenter-excenter lemma. And now we see why it's called the incenter-excenter lemma, because in reality, this circumcircle here also contains the excenter. And a more concise way to state the incenter-excenter lemma is that the midpoint of IA lies on the circumcircle. And this follows by the 9-point circle. So basically, every single incentral configuration involving the incenter and the 3 excenters is just an orthocenter configuration, because I is the orthocenter of the triangle IA, IB, IC, and A, B, and C are the feet of the altitudes. So it's very useful to go back and forth between orthocenter configuration and incenter configuration. Okay, so now that we know about our incenters and excenters, now it seems like a good idea to shift our focus to the incircle and excircle. So suppose that we have our triangle ABC here. So A, B, C. And we have our incircle this time, and it's centered at I. And suppose that the tangency points are D, E, and F. Then, as it turns out, suppose we let BC equals A, CA equals B, AB equals C. Then we have that AE equals AF is equal to, and if we let S equals A plus B plus C over 2, this is known as the semi-perimeter. Anyways, we have that these two lengths are equal to S minus A. Then BF equals BD is equal to S minus B. And CD equals CE equals S minus C. So S minus A, S minus A, S minus B, S minus B, S minus C, S minus C. So how do we exactly prove this? Well, we know that CD equals CE because they're equal tangents. So we know that CE plus EA is equal to B. And then EA plus, because that's FA, plus FB is equal to C. And then BD plus DC, which is FB plus CE, is equal to A. Now, exploiting the symmetry, we can add them all together and divide by 2 to get that their sum is equal to S. And after subtracting each of these guys out, we can end up solving for these lengths here. All right, so let's go ahead and take a step back and let's look at the excircle now. So if I construct the triangle ABC again, I had to erase it because I wanted to look at the excircle now. So now we have our excircle. And suppose that its tangency points are at these new points, which are D prime, E prime, and F prime. So D prime, E prime, and F prime. Then I want you to prove on your own that AE prime is equal to AF prime is equal to S. And then BD prime is equal to BF prime is equal to S minus C. And sorry if this is a bad diagram. Let me go ahead and fix that. So there we go. Then E is closer to here. And then we have CD prime equals CE prime is equal to S minus B. And your goal is to prove this. Thankfully, proving this shouldn't be too difficult given the proof of the incenter lengths earlier, because it's just a very, very similar proof. Instead, you have subtraction now. All right, so you might have noticed that we've seen the length S minus B appear twice, once in the incircle configuration and one in the excircle configuration. And this brings me to one more point that I want to make. So I'm going to clear the rest of these. So if I draw on this excircle now, and only worry about this tangency point up here, E, and also draw on the incircle point, so that's D, then we know that this length here is equal to S minus B, but so is this one here. And therefore, we get the very, very powerful fact that BD is equal to CE. And they're both equal to S minus B. Now, this S minus B part is actually not that useful in the end because we only really care that these two lengths are equal. Okay, so now that we know that these two lengths are equal, let's see what all we can do with the incircle and excircle. And what we're going to be using is homothety. We're going to be using homothety to the most of our advantage. So the first example of applying homothety to the incircle and excircle configuration is when we have the diameter of the incircle. So if DD prime is the diameter of the incircle and D is the tangency point, then as it turns out, if we draw on the line AD prime and let it intersect BC, then we actually end up at the excircle tangency point, and therefore BD equals CE. So how do we prove this? Well, looking at our diagram, it definitely appears that D prime and E are the top points of their circles. So this immediately calls to homothety because the top point is just a relative position with respect to a circle. So D prime is a top point and so is E. So that means that if we take a homothety sending the incircle to the excircle, we'd expect D prime and E to be mapped to each other. And if they are mapped to each other, then that's amazing because A is the center of the homothety because it's the intersection of the tangents. So that means that we have that AD prime and E are collinear. Therefore, it suffices to prove that H of D prime is equal to E, where H is the homothety sending the incircle to the excircle. And this should follow because we have these two top points. But how do we rigorize this idea of top point? Well, if we look at this point E here and look at its tangent, because that's what we have when we have our excircle, we notice that this tangent is just BC. And similarly, we have that the tangent at D to the circle is BC. So that means that if we try constructing the tangent to D prime at this circle over here, then this is parallel to BC. So in other words, we're going from this smaller triangle here all the way to this bigger triangle here. And we have these two excentral tangency points. So they have the same relative position with respect to their triangles. So this point here has the same position with respect to this triangle as this point here with respect to this bigger triangle here. So which means that they all lie on the same line. So we have just used homothety to basically make this proof that these 3 points are collinear very, very easy. All right, now something you might have noticed is that whenever I look at this point E here, we know that BD equals CE. So that means that another way of phrasing it is if we add in the midpoint M of BC, then this is also the midpoint M of DE. So it definitely feels like midpoints are very, very tied to the incircle and excircle configuration. However, we can say even more about the midpoint than just that it is the midpoint of DE when we have E down here. In fact, if we let X be the intersection of DI and EF, where this time E is the tangency point of the incircle with AC, and F is the tangency point with AB, if X is the intersection of DI and EF, then it turns out that AX intersects BC at its midpoint. So how do we exactly prove this? Well, we want to prove that if this is a midpoint here, then AX and M are collinear. So it seemed like homothety worked last time for us, and we want it to work again this time. So instead of saying that AX will bisect BC, let's instead construct a line through X parallel to BC, just like how we did for that one excircle configuration where we use the tangent at D prime. Now we have a parallel line to BC through X. And suppose they intersect at points P and Q. Then if we can prove that X is a midpoint of PQ, then we are set, because then we just take a homothety sending PQ to BC. So now we just have to figure out that PX is equal to XQ. We need to prove that. But now let's try applying certain properties we know about X. Well, one appealing property is that X lies on DI, and DI is perpendicular to BC. And the thing we know about PQ is that it is parallel to BC. So therefore, we have DI is perpendicular to PQ. And this is also DIX. Now, if X is actually the midpoint of PQ, then this actually should remind you about something. This should ring a bell. And this bell it should ring is that this line here is actually the perpendicular bisector of PQ. So if we can prove that DIX is a perpendicular bisector of PQ, we are set. So we know that it's already perpendicular to PQ by default. So if we can prove something like PI equals IQ, then we are set. Now, how exactly do we prove this? After all, we don't really know anything about the points P and Q other than that they lie on the sides AB and AC. So if we want to relate the point I to them, it makes sense that we want to use the sides AB and AC somehow. How does the point I relate to the sides AB and AC? And that's when we remember that by definition, I lies on the angle bisector. So these two angles are equal. So if PI were actually equal to IQ, then that means that I is the intersection of an angle bisector and a perpendicular bisector. And by this logic, you might have noticed that by the incenter excenter lemma discussed above, this point here should ring a bell. And indeed, we proved by phantom points in the second video that if we have the intersection of the angle bisector and the perpendicular bisector, then it lies on the circumcircle. So therefore, we really need to prove that APIQ is cyclic. So here, we need to prove that this quadrilateral here is cyclic. Because if it were cyclic, then I is the midpoint of the arc, meaning PI equals IQ. And then because XI is a perpendicular bisector, that means PX equals XQ, and therefore BM equals MC. Okay, so how do we prove that APIQ is cyclic? Well, here's the one thing we haven't used yet, and it's the fact that X lies on the line EF. So how exactly do we use the line EF? Well, again, we don't really know much about points P and Q other than they lie on the sides AB and AC. So we want to relate F and I to the side AB and AC. And that's when we realize that FI is perpendicular to AB or AP. And EI is perpendicular to AQ. And in hopes that we get another perpendicularity, we remember by looking at this diagram here, remember that's a right angle, that XI is perpendicular to PQ. And we know that XE and F are collinear. So we have three collinear points, all of which are the feet of altitudes. And this should ring a bell. It's just a Simpson line from I to the triangle APQ. And because the Simpson line exists, so Simpson, that implies that the points are concyclic, and we are done. So a forward way of writing this proof, we want to write this proof forwards, is as follows. So first, we construct the points P and Q as shown. Then, because F, X, and E are collinear, and they are the feet of the altitudes, we know by Simpson line that APIQ is cyclic. And because I is the midpoint of the arc, we know that PI equals IQ. And because DI is perpendicular to PQ, we get that XP equals XQ, and by homothety, this means BM equals MC. I just wanted to motivate this proof to demonstrate how we can work backwards from homothety. Oh, and one last thing before we go into the examples. So suppose we have two internally tangent circles here. So let me go ahead and draw this again. And then we have another circle here. Then suppose we have a tangent line here. Then what can we say about this line here? So we have that. Well, as it turns out, this point here is the midpoint of this red arc here, this arc here. So if we label points, then suppose that we let this inside circle be gamma and this bigger circle be omega. Then suppose that they're internally tangent at this point D, and these are points A and B. Then we know that they are tangent at the point E, and line DE meets this circle at point T. As it turns out, we have AT equals TB. Now, how exactly do we prove this? Well, these two circles and them being internally tangent at D should immediately remind you of homothety, because these two circles here, there's a homothety sending gamma to omega centered at D. So if we can prove that E gets sent to T, then that would be amazing. So if we could prove that E gets sent to a point T such that AT equals TB, then we're set. Unfortunately, we don't know much about the point E, other than that it lies on the line AB. So that means that if we take the image of the point E, because homothety preserves parallel lines, that means that the tangent to this new intersection point is parallel to AB. But this can only ever happen if T is the midpoint of the arc. So in other words, by homothety, we have that the tangent at T is parallel to AB, and that implies that TA equals TB. Be on the lookout for this configuration, because it can also be shown in reverse. Because if you have this point, so let me go ahead and clear this. So suppose you have a point T down here, and you have A and B. And you let this be E and this be D. Then by applying this lemma in reverse in a way, we can show that there's a circle tangent to both this side here and this circle here. And the name of this lemma for which AT equals TB is called the shooting lemma. Because you're kind of shooting down from one circle to the other. And it's also called the Death Star lemma in other countries because it's shaped like a Death Star. Okay, that's enough of talking about the shooting lemma. Let's get into an example. Okay, so let's look at our example here. The incircle of triangle ABC touches BC, CA, and AB at points A', B', and C', respectively. The line through I, which is the incenter, perpendicular to the C median, meets the line A', B' at point K. Prove that CK is parallel to AB. So go ahead and try this problem out on your own first and pause the video. When you're ready to discuss, press the play button and we'll discuss it together. So hopefully you've tried out this problem by now, so let's go ahead and solve it together. The first step we must do in any geometry problem, as you probably already know, is to create a diagram. So before we create the diagram, we need to note that this problem is very C-centered because we have the C median, and not A-centered as we usually know it. So we have to be careful when constructing our diagram. Okay, so if we end up constructing our diagram, it looks something like this. So you let CAB be our triangle, and C', A', and B' are the incircle touch points, and I is the incenter. Then the line through I perpendicular to CM intersects A', B' at this point K. We want to show that CK is parallel to AB. Well, let's suppose that our point C prime here, sorry, the point C prime should be over here. Then we want to somehow involve the point M, and because we don't have our excircle, it makes sense to try using the fact that if we draw in this line here, it passes through this point. And that means that this point here, which I'll call X, might be very, very useful. And so might this line IX. So if we look at this line IX, we want to prove that CK is parallel to AB, or in other words, that IX is perpendicular to CK. So we want to prove this. Okay, so what can we say about the point X? Well, we know that the point X does lie on the altitude, and we know that this angle here is also a right angle. So we have the intersection of two perpendicular. So we have a perpendicular from I to CK, assuming the problem statement is true, and a perpendicular from C to IK. Therefore, if the problem statement were true, then it would be that X is the orthocenter of the triangle. So X orthocenter of the triangle CIK. And if we can prove that this is true, then we'd be done, because then IX is perpendicular to CK. So all that's left to do is prove that it's true. And what other way to prove it than just prove that X lies on the other altitude? Because we know that X lies on one altitude because this line here is perpendicular to the C median. So if we can prove it lies on the other altitude, we're set. Now, what is this other altitude? Well, we know that Kx is just the line A prime B prime. So if we can show that A prime B prime is perpendicular to this line Ci, then we're set. So we want to prove now that A prime B prime is perpendicular to Ci. But this should not be super, super hard, because A prime B prime is just perpendicular to this by symmetry, because Ca prime equals Cb prime, and therefore when you reflect it across the angle bisector, it's the same. So that means that it's just that this line is just perpendicular to this line already. So this is obvious. And therefore, because we have these two lines are perpendicular, we have that Kx is perpendicular to Ci, and also Ik is perpendicular to Cm. And this means that Kc is perpendicular to Ix. And this implies that AB is parallel to Kc as we need. So the point of this problem is to recognize the configurations when you see them, and note that recognizing these configurations can save you a lot of time. Okay, so that's it for this video. Thank you so much for watching this, and I'll see you guys in the next video for the final video in this series.